Hello. Yeah. What happened to Anjali? She is removed automatically. Do you have some problem? Okay, so 18 people are here. We are expecting some more. So first thing is your second series will be scheduled from 13 to 16. 13th is the second Saturday, 14th is Sunday, 15th and 16th because we are arranging exams like that. Because of the reason we may not lose some academic time, and we are planning to cover the entire syllabus before 20th. Okay, so we will have a regular class on 17th, 18th, and 19th, and even 20th. With that, I hope we can cover the syllabus. 13th will be nano electronics, and 14th will be advanced communication. 15th, departmental elective, that is cybersecurity, there's LOPO, ELS, and all the things. I'm not sure cybersecurity is in the global elective or okay. Anyhow, it is class elective 15th. 16th it be global elective. So we will start the class now. Just 1 minute. There's certainly a problem there. So can I start? It's visible here. That slides. Okay, thank you, Akila. So now we want to discuss how to implement different logics in pass transistors. The simple method that normally we are following is, I told yesterday, we can express the truth table as a function of input. Or other method that is normally people following is draw the K-map. In K-map, we can identify that for B is equal to 0 and B is equal to 1. That is for an AND gate. There will be a condition that is marked as C1 and C2. That is when B is equal to 0, always output is 0. And B is equal to 1, always output is 0 for A is equal to 0, 1 for A is equal to 1. That means you can say it is A. So C1 is equal to 0 and C2 is equal to A. So we will implement like this, that is B bar, that is 0 of B. Then what we wanted is B itself. Then when B is equal to 1, B is equal to 1 means we can directly apply B to the gate, and that time we need A. So output is AND. Similarly, if you are moving to the second gate, that is an NAND gate, when B is equal to 0, output has to be 1, that is C1 is 1. When B is equal to 1, output is the inverse of A bar. So we are taking B is equal to 0. That is the first transistor. Gate is connected to B bar because gate has to be enabled, means you have to give B bar, that is on. Then B bar itself is given. Instead of that, if you want, you can connect a 0. Then second transistor, the B is driving. During B, output has to be A bar. That is, A is equal to 0 means output is on. A is equal to 1 means output is 0. So it is driving, that you will get an AND gate. Similarly, if you want to go for a OR gate, just 1 minute, there is some request. Nothing is pending. Okay. Okay, that OR function, if you want to check, you can draw the K map, then find out that B is equal to 1 and B is equal to 0. B is equal to 1 means output is always on, that is C1 is on. B is equal to 0 means output is A itself. That is, if A is equal to 1, output is on. If A is equal to 0, output is 0. So by driving B, you have to transfer B itself. By driving B bar, you have to transfer A itself. So that is an OR gate. Similarly, you can go for a AND gate. The same thing can be if the inputs are reversed, that is, and you just check inputs are A and B, and NAND gate it is B bar and A bar. Similarly, for an OR gate it is A and B, A bar and B bar. So such a way we can implement AND and NAND, OR and NOR in a same circuit. Now take an XOR operation. XOR can be implemented, that is both the things are shown here. That is how an XOR can be implemented. XOR output can be implemented as a function of A or a function of B. That is, if you are checking B, in case of B as the control, if you are taking B as the control, then you can identify that B is equal to 0 means A is transferred. B is equal to 1 means A bar is transferred. So B is equal to 0, driving with a gate, it has to be driven by B bar. That time A is transferred. When B is equal to 1 means B itself drives it, and in that time required output is A bar. So it is connecting like that. Similarly, the same circuit you can express as A as the control signal and B as the input signal. So you have to analyze reversely. You just check A is equal to 0. You can identify that output required is 0 and 1. That 0 and 1 is corresponding to B. So A bar, sorry, it is X NOR. X NOR means you have to go for the reverse. So A is equal to 0 means output required is 1 and 0. 1 and 0 means B is equal to 0, output is 1. B is equal to 1, output is 0. That means it is B bar. And A is equal to 1 means output requirement is 0, 1. 0 for B is equal to 0, 1 for B is equal to 1. So it is B, that is an XNOR implementation. Now if you have more than one gate, sorry, more than two inputs, A, B and C is there. So you can take a condition A is equal to 0. Then A is equal to 0, can identify that all outputs are 0. So A is equal to 0 is driven by sorry, that is a combination of AND and NAND. I want to just check 0, 0, 1, 1, and 0. So this functionality is AND, that is the K-map given is for AND. So take a AND side. AND side what is given is when A is equal to 0, output has to be 0. So for driving A is equal to 0, you have to take A bar and give it to the gate. That is the first transistor. So connecting to A that time it is 0. Then second condition is A is equal to 1. A is equal to 1 means if B is equal to 0, output is 0. If B is equal to 1 means output is C. You can see that. But this is just check when A is equal to 1. The requirements are it becomes 0, 0 when B is equal to 0. If B is equal to 1, it becomes C. So you can write it as C bar B and B C. So if you are checking A, it is A is driving a C bar, and again it is multiplied by B into C bar. A is driving a C, and it is again driven by a B. It is A, B, C. That is, if A, B, and C is on, output become on. Now we are going for the third case. That is when B bar is on, what will happen? When B bar is on or B is equal to 0, we have to transfer B itself. So a B bar driving, output is B. That's a NAND gate, 3-input NAND gate. Now, what is the problem that we are facing with the NAND? The pass transistor logic is, we told already, for a NMOS, the output is not a strong one. You cannot realize a strong one. And for a PMOS, you can not realize a weak zero. That is, zero will be not zero voltage. Instead of that, you will get VT. So this is the problem you have when going to cascade. It is you just check. The first one is VDD and VDD. So output is VDD minus VT. That is driving the next transistor. It is again biased with input is VDD, but gate drive is VDD minus VT because it is the drive of the previous stage. So naturally another VT is reduced there. So it becomes VDD minus 2 VT. Again a VDD that is driving another transistor with the VDD as the input. But again you have to consume a VT there. So total output becomes VDD minus 3 VT. And the VT in the sections of started portions, I told what is the minimum criteria or the criteria that we are using for fixing VDD and VT is VDD is most of the time it is 2 to 4 times of VT. So VDD minus 3 VT means approximately output will be treated as zero itself. Because if you are even if you are taking it is VDD is equal to 4 VT, 4 VT minus 3 VT is VT. That is the highest. This is for 1. Now you take a PMOS switch. PMOS switch 0 is VT. So a PMOS switch and NMOS switch have the same voltage for 1 and 0. This is a problem that you are going to face when you are cascading pass transistor logic. Arjun, okay. A solution for this is we will go for a transmission gate logic. What is a transmission gate is, one thing is CMOS, you know. What is CMOS is complementary MOS. When a PMOS is created, default and NMOS will be generated. Or when a NMOS is created, default a PMOS will be generated because it is appears in pair. So if you are using a PMOS in your entire buffer area, a NMOS is not used or again used or not, a NMOS will be there. So we are utilizing that property, that is we are pairing or we are combining a PMOS and NMOS. Then what will happen is PMOS has to driven by 0 and NMOS has to driven by 1. So a control signal C, it has to be connected to NMOS. Then you have to take the C bar and that has to be connected to the PMOS. Then only at the same time the NMOS and PMOS will work. So how it works is, there is, we know NMOS have a problem of high case and PMOS have a problem of low case. That is, you take A as VDD, that is 1. Drive is there, that is, drive is there means C is equal to VDD. So naturally C bar is equal to 0. Then output, what is the condition we want to get is output has to be on, that is VDD. So we will first check A is equal to VDD means that is the highest point. So naturally A will be the source for the PMOS and source for the NMOS is lowest point voltage, that is B. So VGS is equal to the potential difference between A and C bar in PMOS and VGS is equal to the potential difference between B and C in NMOS. So now A is equal to 0, A is equal to 1, that is VDD, C bar is equal to 0, VGS of PMOS is equal to always VDD because A is not changing, only B is charging or discharging. Now you are going for B, VGS of NMOS. VGS of NMOS is the potential between B and C. C is VDD. B is equal to 0 at start. It charges to VDD minus VT. That time the VGS is equal to VT. So further the NMOS become off. So normally if a NMOS is only present there, what will happen is the capacitor cannot further charge, but this case, parallel to that a PMOS is there, but PMOS VGS is still A, with the potential between A and C. A is not changing VDD, C bar, sorry, A and C bar. A is VDD and C bar is equal to 0. So VGS is now VDD, that is greater than VT. So the path through the PMOS is still on for charging further up to VDD. So the output B can charge up to VDD. Similarly, if A is equal to 0 and B has to discharge, the discharging will be stopped by PMOS when output become VT. Further, it cannot discharge. But in the case of NMOS, the source is output. Sorry, source is the lowest point. Lowest point is anyhow it is the input A, that is 0. So VGS is equal to C, the potential difference between C and A for the NMOS, that is C is equal to VDD, A is equal to 0. So naturally it is VDD. All the time the NMOS is on, so it will discharge further to 0. So we can avoid the problem of weak 1 and strong 0. Okay. Now this is the condition that we stated previously. Now this is how the discharge and charging mode of discharging mode of B, that is from A is equal to VDD. It is clearly written here, A is equal to VDD, C bar is equal to 0, C is equal to VDD, and A is equal to source for PMOS and B is equal to source for PMOS. So that voltage VDD minus 0 is always there. Similarly, if you are going for discharging case, A is the source for NMOS. So NMOS VGS is equal to A and C, that is 0 and VDD, both are constant, so it will permit a full discharge. Okay. Now, how to implement a circuit is, you can implement something like this. So first thing is you can write a truth table and express a function as variables of 1 or 2 inputs. Second thing is you can implement the function as it is. But the thing that you have to cover is some functions not covered that you are taking as the input has to be recovered. That is, in this case, we are taken as S1, S2 as the input and S1, S2 as the control and AB as the input. So first term is A, S2, S1 bar. So we are taking A, it is driven by S1 bar and it is driven by S2. So that will give the first top 2 combinations will give a function that is AS2, AS1 bar. The second line, it will give B S1 bar. Then next time is B S2 bar. So that line will be S1 bar, S2 bar. Then you will get a 1, that is the third term is independent of A and B, but it is an 1. That is the case S2 bar and S1. So 1 is controlled by S1 and S2 bar. Now the condition is you have to implement a condition that is 0. What will happen if a combination of, that is the combinations that you are covered is S1, S2 bar, sorry, S1 bar, S2 bar, that is 0, 0. Then S1, S2 bar, that is 0, 1. Then S2, S1, that is 1, 0. Now the unconditioned or uncovered term is actually S1, S2. So S1, S2 means if you are not providing a path for S1, S2, what will happen is if that condition rises, the previous state will remain. So to avoid, because if S1 S2 rises, you have to discharge the capacitor. That's why we are providing the fourth path that is driven by S1 and S2 that is connected to 0. So this is a method that we are normally adopting for implementation of fast transistor logic. Then your syllabus have another term that is, so with this we are completing fast transistor logic. From here, that is when you are using a PMOS NMOS combination, it is called a transmission gate logic or complementary gate logic. Now we are going for pseudo NMOS inverters and pseudo NMOS logics. Pseudo NMOS is in a normal, okay, I will take that normal figure and explain what is the difference. Just 1 minute. Actually, this is a normal inverter circuit or static CMOS inverter circuit where the PMOS and NMOS devices are driven by the input. The PMOS is called pull-up device and NMOS is called pull-down device. PMOS will permit to charge and NMOS will permit to discharge. If the charging has to be recurred or the discharging has to be recurred will be decided by the circuit. We can, or the combinations. We can take the circuit, that is it for an AND gate. It is a product, so there will be a parallel combination at the top and series combination at the bottom and negative logic is realized. But instead of using this, okay, can you see the slide now? Somebody can feedback. Someone can give a feedback. Can you see? Okay, thank you. So what is the difference is there is no pull-up network. Instead of that, the PMOS is one PMOS is there that is permanently grounded. The gate of the PMOS is permanently grounded. The source of the PMOS is at VDD. So VDS of the PMOS, VGS of the PMOS become VDD minus 0, that is VDD, or it is minus VDD, we are not taking the sign. So VGS is equal to VDD. Now it is greater than VT. So the PMOS is always on. Always on means it will always try to charge the capacitor. And what is the condition of the PMOS? So we have to take VGS and VDS. VDS is equal to V out minus VDD, and V out minus VDD is always less than VDD minus VT, that is VGS minus VT. So this will be in saturation. So this transistor is always in saturation. And the transistor will be driving the capacitor all the time. PMOS is driving the load capacitance CL all the time. And when the capacitor want to discharge, this case is a NOR gate. That is, if A, B, C, and D, or otherwise it is a NAND gate, that is input 1, 2, 3, and 4. is in parallel. When all the inputs are 1 for a NAND gate or any one of the inputs are 1 for a NOR gate, the output becomes 0. So what is the condition is one of the transistor NMOS is on, the capacitor will start to discharge through the NMOS. The same time the capacitor is charging through the PMOS. If the design is such a way that the PMOS charging is weak and NMOS charging is strong, NMOS discharging is strong, then the discharging will exceed the charging and the capacitor will goes to low voltage. All other conditions we will get a high voltage. But what is the problem is the output is 1 is always VDD, but output 0 is never be 0. Instead of that, it may be an voltage V1. That V1 will be decided by the factor how many transistors. That is, if you take NOR gate, if A, B, C, and D is on, then naturally you will get a lower voltage very near to 0 because the discharging current is very, very high. It is 4 parallel transistors are trying to discharge. If you take A alone is on, that case also it is discharges, but the current through the A is low. So if the charging current of PMOS and discharging current of NMOS is the same, then output will be settled at VDD by 2. If charging current of PMOS is only half of discharging current, then output will be settled at VDD by 3. Similarly, depend upon this strength, the current strength, the 0 of this pseudo-resistive NMOS inverters or NMOS circuits, it is not an inverter actually, it is a NOR gate and NAND gate. Inverters or pseudo-resistive gates, the outputs will be never be settled to 0, but it have a strong on a weak 0. Weak 0 means voltage will be always higher than 0. So with this, we will cover 4th and 5th modules. I hope we can stop here because I have another section that is adiabatic circuits that have some slides, but adiabatic circuits we can cover after the examinations. For examination point of view, the questions will be from 4th and 5th module. So I'm stopping here. If you want to discuss anything, now we can discuss. So the 6th module we will try to cover on 17th and 18th. Any feedback? Hello? Okay. So all the best. You have examinations on 13th, 14th, 15th, and 16th. And your advisors will inform the timing of examinations. Our exam will be on 15th. And you can expect questions only from whatever the portions we are covered. Okay. We will continue on next on 18th. Okay. Thank you.